In this video, I want to talk about arc length and how we can use the integral to find the length of a curve like this. So first I want to begin with kind of deriving the formula to see how we get it, because I think it's fairly intuitive once you see it broken down. You won't need to remember how it's derived, but I think it's useful to see where this integral comes from. I think that it's better to understand where formulas come from than to just have them handed down from on high and then try to use them. So I've just drawn a little curve here, and I'm going to call the curve f of x, and I'm going to show you how we kind of begin. So if we kind of put this, maybe on the x-axis, and we pick a few points. So let's call this like x1, and we might call this x2. Try to keep them somewhat evenly spaced, although that's not strictly necessary. So call that x4. So we're going to get these points here, right? So here's a point on the curve, here's a point on the curve, here's a point on the curve, here's a point on the curve. And what we're going to do is basically estimate this by taking these lengths. So maybe I'll do that in a different color. So there's that one. Here's another one. Here's another one. Obviously, the flatter the curve is, the better the approximation is. But we call this, maybe like, well, let's just focus on this one here in the middle. So what I'd like to do, one way to think about this is I can draw a little triangle in here, right? And if I can find this distance and this distance, if it's a right triangle, then I can find, I'm going to call this L for the length of that. All right, so we're just going to focus on how to find the length of one of them initially, and just understand that we could have as many of these as we like along the curve. We can put in more in between. I just kind of space these out this way. So we're going to call this distance between any two, we're going to call it delta x. And it doesn't necessarily need to be the same, but just for the sake of this derivation, I'm going to say that it is, that there's this distance from it's x3 minus x2 is my delta x. And then this vertical distance right here, well, that would be f of x2, right? So the function value associated with x2, and this one right here would be f of x3. So this vertical distance is f of x3 minus f of x2. Of course, we don't have to always assume the other one is bigger than, we can basically kind of, we'll see actually why, but this difference doesn't necessarily, we could take an absolute value. We don't have to assume that f of x3 is bigger than f of x2. Okay, so then since we have a right triangle, then we know that we can use the Pythagorean theorem. So let's let L equal the square root of, so the one side, right, we want the hypotenuse here, so it's the square root of this side squared plus that side squared. So that's delta x squared plus, I'm going to have f of x3 minus f of x2 squared. Okay? So that's what we start off with. Now, the mean value theorem, and we studied this in 251. Basically, what it says is, I'll use another color here, so that somewhere in between x2 and x3, if this is a continuous and differentiable function, so the derivative has to exist for all these points in here, but somewhere in between x2 and x3, there is going to be a point where the tangent line is parallel to the secant line. All right. In other words, if we take f of x3 minus f of x2 over x3 minus x2, you see that that's just the slope of this secant line right here from x2 to x3. So there's a change in y, the rise over the run. And the mean value theorem says that there is a point somewhere in here, it would be this point here, so like right here, we'll call it C. Basically it's saying that there's a point that if you take the derivative at that point, then the slope of the tangent line at that point is equal to the slope of the secant line at that point. And then this can be rearranged so that f of x3 minus f of x2, in other words, if you multiply both sides by x3 minus x2, right, and do the same thing over here, I get f prime of c times x3 minus x2. All right, so we can't, but remember, what is this? Well, we said that difference right there this is delta x. All right, so it's actually f prime of c delta x. So what we'd like to do is take this right here and replace it with that. So, continuing our derivation, we have that L equals the square root of delta x squared plus f prime of c delta x, and this whole thing was squared, so this is squared. Now, of course, if a square of a product, this is equal to f prime of c squared delta x squared. But now I have a delta x squared in both of these terms, so I can factor that out. So if I pull out my delta x squared, I'm left with a 1 here plus f prime of c squared. Okay, now a property of the square root is that the square root of the product is the product, oops, that's a delta x. The square root of a product is the product of the square root, so I can rewrite this as 2 square roots, 1 plus f prime of c squared, which is, well, the square root of delta x squared is just delta x. So this is looking a little bit cleaner, right, than what we started with, which was kind of a mess. Okay, so that's what we can also put the delta x on the back, and we'll see why we want to do that in just a moment. But notice that this is just one of these, all right? So let's call it, I don't know, since it's in the second interval, let's call it L2, all right? So we just found L2. But if we had like a whole bunch of these, or we had more points, then the length of the whole thing would be, the length of L1 plus the length of L2 plus the length of L3. That absolute value we're just kind of using that as kind of the length, right? That's what we mean. And then up to, we might have n of these. All right. Well, that is going to be the sum. So each one of these is going to look like this, except it's going to be, we're going to have some kind of a subscript on there, right? So really this would have been delta x1, or in this case actually it would have been delta x2, all right? And this would have been f prime c sub 2, because this we could call this c sub 2 because it's in the second interval, and there'll be a c in the first that we would call c1, and we'd do one in the third interval that would be c3. So we're going to sum these up, all right, from I equals 1 up to n, because we have n lengths that we're adding up, and it's going to be 1 plus f prime of c sub I, that just means whichever interval we're in, we take that point, squared, and then delta x I. And that just means that this distance doesn't have to be the same all the time, right? The distance between these might be different, so it might be delta x might be one thing for the first interval and a different thing for the second interval and a different thing for the third interval. All right, now this summation, what we want to do in order to get this arc length exactly is let the number of intervals or the number of lengths go to infinity, right? We want to take the limit as n goes to infinity of all these, and then that will give us the arc length exactly. Now, we might say that this thing, if we wanted to say that it started at A and out here it ended at B, so we want to find the arc length from A to B on this, then this limit gives us an integral. It gives us precisely the integral from A to B of the square root of 1 plus the derivative of the function squared. And when we take this limiting process, remember this delta x, that's the width of our intervals, and it basically goes to, goes infinitesimally small, and we call it dx. So that's where the dx comes from, the delta x. All right? Okay, so this is our arc length formula, and I'm just going to do 2 quick examples to see how we would use it. All right, let me get that out of the way. All right, so for the first example, let's let our function equal 3x plus 1, and we want to find the length of this curve from 0 to 3. All right, so our formula, we're going to integrate from 0 to 3, and it's going to be 1 plus the derivative of this function squared. So the derivative of 3x plus 1 is 3. So squared, y prime squared, is 9. So I have 1 plus 9 dx. All right, well, this is the integral from 0 to 3 of the square root of 10, which is just a number, so we get square root of 10 times x from 0 to 3. That's square root of 10 times 3 minus square root of 10 times 0. We usually put the 3 out in front, so it's just going to be 3 square root of 10. In this case, that's a line, right? So let's just verify this geometrically. Let's say I want to graph this thing. So we know the y-intercept is 1, all right? And then at 1, it goes up to 4, so there's 4. And at 2, it goes up to 1, 2, 3, 7. And at 3, it goes up to 1, 2, 3, 10, right? So our line is going to look like, let's see if we can get this point right here. And we're here, so it's going to look something like this. Right? And what we're trying to do is we want to find the length right along here. All right, we want to find that length. All right, but we're working with a line here, right? So we have other ways to do this besides using the arc length formula. Let's just draw in a right triangle. Okay, now we know the length of this side is 3, and from 1 up to 10, the length of that side is 9. So now we can just use the Pythagorean Theorem, right? So we're going to have the square root of 3 squared plus 9 squared, which equals the square root of 9 plus 81, which is the square root of 90, which we could rewrite the square root of 9 times 10, square root of 9 times the square root of 10, which is 3 square root of 10. Exactly what we got before. Okay, so that was a very straightforward example. Let me just go over one more example on